Good morning, ladies and gentlemen. May I have your attention, please? Thank you. At this time, I ask that you raise your hand if you did not get red mark for today, the 23rd of September. Is everybody good? Great. So as promised, you will receive your test back today so you can see exactly how you gained or lost partial credit. I picked some key areas here where some students lost points in both sections, and so I'm going to go ahead and point those out as we go through and have our discussion for your Bellwork today. The second question then is a setup for what we'll be after today for our content objective. We're going to develop the calculus definition in the next two class periods for instantaneous rate of change and the derivative. And so you've seen the notion of derivative in pre-calculus and an FST/pre-calc compacted. We're going to go ahead and develop the calculus definition, one of them over the next 2 days, and then finally an alternate definition will be developed, and we'll be able to use and apply and decide which definition is better depending upon what it is that we're working with. And so I'm super excited about that. But first, let's go ahead and shore up some of our limit evaluations. So non-calculator, we always want to try with initial substitution of that x value of concern, and let's see what we're working with. So upon direct substitution of my x value of concern, I get square root of 4 is 2, minus 2 is 0. All over 4 minus 4 is 0, so I get an indeterminate form. Right? We can't tell what the value of the limit is or isn't simply by looking at it. That's okay. We're going to go ahead and dig into our algebraic tool bag, right? Though duct taped and tattered worn it may be, and rewrite that expression, right? Hopefully in such a manner where the x value of concern is in its domain, and then we can evaluate through direct substitution. And that's what the limit theorems are all about, right? That's why the limit theorems are important in the first place. So what might be an appropriate tool to try here? Joel? Thank you. We'll multiply top and bottom by the conjugate of that radical expression. So if we're to multiply top and bottom by the conjugate, that is the same terms but opposite operation, that would be root x plus 2. Root x plus 2 both top and bottom. And now we'll go ahead and distribute, right? We'll multiply these two binomials together on top in accordance with kind of our FOIL mnemonic or double distribution, and make sure that we're keeping that limit expression here, right, throughout. Some people lost points for notation on their test if they drop this limit notation. That's what allows us to cancel out that factor ultimately so that we're able to evaluate this algebraically. So here we go first. Outer, inner, last, all over, and then don't distribute. Some people got stuck on this one because they did the FOIL process on bottom as well and created multiple radical expressions. We want to leave this in factored form in the hopes that we'll be able to cancel out with the recurring factor on top. So we're going to leave this as quantity x minus 4 times quantity root x plus 2. Awesome. Combining line terms on top allows the rewrite. Now because we've created a common factor on top and on bottom, and because we're evaluating a limit, because we have rewritten that expression, LIM, the limit as x approaches 4, we don't care what the value of the expression is when x equals 4, in fact x doesn't equal 4, and that allows us to play the cancel game. Now we can rewrite, still have the limit as x approaches 4, and for the first time our rewritten expression, right, does include 4 in its domain, so I can evaluate through direct substitution. Notice how this is the first time we've dropped the limit. No longer do we need the limit. We did need it up until now. So I get 1 over square root of 4 is 2 plus 2, so I'm getting 1/4. And I saw many of you already had this. Go ahead and raise your hand if you already had 1/4. Great news, you guys. Awesome. Let's go ahead and take a look at the second. So my second limit, it lets x approach negative infinity. And so we saw that all the tools we've learned from pre-calculus still hold true now in calculus. One of those tools is in constructing an end behavior model, and it doesn't require one of our algebraic techniques like multiplying by the conjugate, right, like Joel provided, or factoring, or synthetic substitution, right, or common denominator. In fact, we can just develop an end behavior model so long as x is approaching one of the infinities, positive infinity or negative infinity. We don't have to do an algebraic technique here. But what allows us to do that again is the fact that we're letting x go to positive infinity or negative infinity. So some people on the test constructed an end behavior model just because they had a rational function, right? But x was approaching a particular value, like -3. That's not helpful, that's not useful, and that's not okay. We only construct an end behavior model if x is going to one of the infinities, and we're looking to the far ends of the graph. And so let's go ahead and construct an end behavior model. Because x is approaching negative infinity here, and I know we can construct said model by considering the quotient of the dominant terms on top and bottom. Make sure you grab all of them. Another place people lost points is they didn't grab all of the dominant term, including signs. And so when you go and grab the dominant term, this cubic term, that includes the negative, right? Who does that negative belong to? Does it belong to the linear term or the cubic term? It belongs to the cubic term, so you better grab that when we take the dominant term. All over the dominant term is the cubic again. So there might be asymptotes in the middle, there might be squiggles, maxes, mins, right? However, as I look to the far ends of the graph, it appears as though there's a horizontal asymptote. My function values are simply going to approach the y value, y equals -3/2. So without any algebraic techniques, you're dividing every term by the greatest power of x that appears in the numerator or the denominator. We've been able to determine the value of this limit is -3/2. Raise your hand if you already had that. -3/2. Woohoo! Good job. And lastly, to set up for today, if we're considering the slope of the line connecting 2 points on the function, right, that's what's going to be called a secant line today. The secant line goes through 2 points on a graph or connects 2 points on a function. In this case, we're going to connect our old school notation, x coordinate, y coordinate, with our new school notation, a and f at a, or b and f at b, in order to construct our formulas for average rate of change and eventually instantaneous rate of change. So first, I better figure out the points on the function. When x is 1, it appears as though y is given by 7 minus 1 squared is 7 minus 1 is 6, so I'm getting 6. And at the point when x equals 4, it appears as y is given by 4 squared is 16, 7 minus 16 is -9. Did I do that correctly? -9? Awesome. So, how will I calculate the slope? What formula can I use to calculate the slope, Megan?
-9 minus 6 and 4 minus 4, 4 minus 1.
And where is this coming from? Right? Where are these numbers coming from, Megan?
The slope formula y2 is y over x2 plus x.
Awesome. So our age-old slope formula back from Algebra 1, right? The difference between the y coordinates, that's our vertical change between points, our rise over x sub 2 minus x sub 1. Thank you, Megan. That's our run, our distance between the horizontal coordinates. And so if we call this m for slope old school, we get this, and then we could simplify, of course, -9 minus 6. I'm getting -15 over 4 minus 1 is 3, so it appears as though we generate a slope value of -5. Raise your hand if you have -5 for the slope connecting those 2 points. That's great. So we just done a secant line slope calculation, and we'll be doing that throughout today's activity. However, we're going to do it now as an average rate of change, as we can consider, right? We consider the rate of change of a quantity with respect to the independent variable, and that's going to be the basis for our development of the derivative, which I'm super excited about. You know, we saw those last 2 days in Unit 2. We're really kind of starting to drag on because I was getting so excited for our upcoming Unit 3 and derivatives. We're finally going to be able to do stuff, right? To do stuff with our calculus, and so I'm very excited about that. Okay. At this time, we're going to go ahead and do 2 separate homework checks. So I'd like for you to take out your review OTL. We did not collect that on test day because we want to make sure you have plenty of time for your exam, the same amount of time that the 8A class had. So at this time, please take out your review OTL number 5 only. We're not turning in Unit 3 OTL number 1 at this time. We're only turning in the review. Please give yourself credit for those you completed out of 19. If you kindly staple multiple pages together, there's a stapler on the front table and a stapler on the side activity table. Please staple multiple pages together so they don't get lost and get credit for the hard work you're doing outside of class. After giving yourself credit for those you completed, divide, enter, multiply 2, and box that into the canvas score nice and big on top, please, down to the nearest half point. Also make sure that your name, first and last, 1B, and number 5 will review are clearly labeled on top of your OTL. After a final check that you've got all the key pieces on top of your assignment and stapled together, please pass from the back to the front row to make sure they're facing the same direction. That'll be awesome. I appreciate your help. This is your review OTL only. Thank you, guys. Good with review OTL number 5. Thank you. Then at the same time, we'll go ahead and do a second separate check, and that is Unit 3 OTL number 1. So this is your first OTL from Unit number 3. On the Moodle page I took off, on the schedule, I took off that C4, and I since changed it from the hard copy. And so I'm glad that you grappled with C4. If you did, I decided not to include it next year. So I did take that off. We'll go ahead and give yourself credit for those you completed out of 20 for this one, out of 20. Divide, enter, multiply by 2. And again, give yourself an independent canvas score, please. Box to the nearest half point. 0 to 2. Again, please make sure that your heading first and last 1B and number 1 are clearly labeled. This will be a separate turn-in from our review OTL. Again, please staple multiple pages together, do a quick check that is properly labeled and scored, and then pass from the back to the front. Thank you, front rowers, for your help. I appreciate that. You make sure they're facing the same direction. It's a lot easier to record. Strong work, ladies and gentlemen. I appreciate your help. At this time, I'd like to share with you your test score. Okay, and so I'm going to go ahead and pause the recording while we have our test discussion. Okay, so we'll go ahead and resume our discussion. What I want to do is go ahead and develop the calculus definition for instantaneous rate of change. You guys already have a wealth of information and foundational knowledge at your disposal. So we're going to investigate this by considering average rate of change calculations today, and then developing instantaneous rate of change. On your way in, there is an opportunity to pick up a ruler. The rulers aren't very good. They're the cardboard cutouts from WKC, and so if you have your own plastic ruler that's longer, that might be useful. One note before we get going on the activity. One question you're asked to construct a tangent line. Okay, and so as you're looking at this function, where we're talking about the diver, right? The height of the diver above water as he goes off the platform diving board. Recall that a secant line connects 2 points on the curve, just like your Bellwork number 2. And so in our Bellwork number 2, we considered the slope of a line that connected 2 points on a curve. This line in blue would be called a secant line. You're going to do separate secant line calculations in today's activity. However, we're going to then draw a tangent line, and we'll select 2 points along that tangent line in order to do a final slope calculation to get an estimate for instantaneous rate of change later. I just want you to know that a tangent line touches the curve. It comes from the Greek tangent, to touch. Just like in geometry, right? A tangent to a circle, just touch the outside of the circle at one point and balance on it. So you can think of like a basketball and taking a ruler, right? And trying to balance that ruler on the outside of the basketball. The same is true when you draw your tangent line in today's activity. You can't cut into the curve, just like that ruler wouldn't sink into the basketball or cut through 2 points in the basketball. It would balance on the outside of it. So you're going to draw a line such that it just touches the curve in that 1 point and doesn't cut through it. And so something like that. We don't want to have your tangent line cutting into the curve, right? We don't want to have your tangent line cutting into the curve on either side. Otherwise, it would become a secant line, right? Because it now go through 2 points on the curve. So we're trying to just touch the curve in 1 point, and that's going to help you. Now, when you go to calculate its slope later, you don't have to necessarily use points that are on the curve. If you want the slope of that tangent line, regardless of where it is, you can select 2 points on it, anywhere on it. Right, on the curve, that happen to be on the curve, or otherwise, you could pick 2 points. Just try to pick ones that are kind of farther away. So if you pick 2 points that are farther away, you're going to get a better approximation. And so that will be a nice setup and help you go through the activity with more success within your group. Stamp eligible items include number 4, number 9C, number 10D, and summary number 4. Make sure that you guys are agreeing and following along. Several of these are numerically important. In other words, in order to get your stamp, you have to be accurate on that, so please pay attention to detail and include units. Yesterday, some groups were forgetting to include units. As we apply our calculus concepts in context now in Unit 3, it's very important that we're referring to the units, right, within the question so that our answer has meaning in the context of the problem situation. At this time, we'll go ahead and scoot into our proper voting groups. I'm going to pause the recording, and then we'll come back together for our closure with about 7 minutes to go, okay? Thanks for getting started right away. I appreciate that. Thanks for your OTLs, and I'll be around momentarily. At this time, I ask that you stop looking at your OTL and then find your summary from the activity, because I'll be calling on you to share your responses with the entire class. So we wanted to get out of here, right, get out of this activity, a formula that gives us the average rate of change in some y quantity with respect to the independent variable quantity. So what would our formula for calculating the average rate of change between 2 points on the interval a to b for some function y equals x? And let's use our notation with f, right, function notation, and a and b. What would that look like as a formula? Grace?
Y equals a minus y equals f of b minus a.
Good, so f of b minus f of a all over b minus a, and we could call this then a formula that gives the average rate of change. So I'll just label that as the average rate of change on that interval a to b. Thank you, Grace. Raise your hand if you had the same formula. So f of b minus f of a all over b minus a. Excellent, and that's just our old school slope formula, y sub 2 minus y sub 1 all over x sub 2 minus x sub 1 in disguise with new notation. How is the average rate of change shown graphically? So what's shown in the graph, right? What is that average rate of change formula showing in your picture? Finally?
The secant between 2 points and then the slope of the secant.
Absolutely, and so that average rate of change calculation is calculating the slope of the secant line between those 2 points. And so that would be the slope of the secant line connecting the points. And I'll use Grace's points, a comma fa and b comma ff. And also highlight that key quality. We're calculating the slope of that secant line that connects those 2 points. Awesome, thank you. How do you find an estimate for the instantaneous rate of change? The instantaneous rate of change at a single point, x equals c, for some function y equals f of x, right? And so we have 2 different ways for doing this. And so what was one thing we did your first stamp? What was one thing we do when we're after your first stamp there? Blake? Yeah, we'll use close values to my point of concern, absolutely. So to get an estimate for the instantaneous rate of change, we could do it in one of 2 ways. Our first way would be to do average rate of change calculations or secant line slope calculations for successively closer points to my point of concern. So we can do So one method would be to perform slope calculations, all right, secant line slope calculations using points closer and closer to the point of concern. The other way was our next stamp, method 2. What did you guys actually draw then for method 2? Katie?
Tangent line on the ground.
Absolutely, we could draw a tangent line and then calculate what about that. Good, and so the second method would be to draw a tangent to the curve at that point of concern. And then calculate its slope. Awesome. And lastly, how are we seeing those approximations? How are we seeing those approximations graphically? So then what is the instantaneous rate of change shown graphically? And that was our summary number 4 then. So what were we seeing then? Andy?
Slope of the tangent line.
Good, the slope of the tangent line. That is the limit of the secant line slope values as you use closer and closer points to the point of concern would yield the value of the slope of the tangent line. Nice job, you guys. All right, so our final ranking, here we go. Be ready, you're gonna share with the class. Is the instantaneous rate of change negative, positive, or 0 at each point? So here we go. At letter A, 0 positive or negative slope. Go ahead and share with the class. Scott?
Positive.
I gotta go positive as well. We can see that a tangent drawn to the curve at point A would have a positive slope value. At letter B, is this positive, negative, or 0 slope? James?
Negative.
Negative. Thank you. We can see that a tangent to the curve drawn at point B would have a negative slope value. Oh boy, I'm gonna go for it. Ooh, don't like that as much. Tough stuff. Oh yeah, there we go. And lastly, at C, would the value, right, would the value of the instantaneous rate of change be positive, negative, or 0 for that? Colin? 0. I've got to go 0 as well. It appears at this point, right, that the y values are neither increasing nor decreasing. The slope of the tangent would be 0 at x equals point C, right? Awesome work today, you guys. So you've done a great job. Now we've got a chance to get some of this done while you're still in class, so you can work in your partner pairs now that you put the desk back. Great work today, and I'll go ahead and stop the recording now. Way to go.